Hello everyone. My name is Emanuel. I work at Next42, one of the supporters of City.AI, on AI-related stuff. Today, though, I wanted to talk about what I did at my previous job, which was about applying AI to 3D, one of its more unusual applications. About my experiences with that and current challenges and limitations that we had and problems that we were facing. But before that, I wanted to show you a picture. So, any ideas what this thing here is? No, not a filter. Lego. Not a Lego, no. Sorry? What was that? I didn't hear that. No. Actually, what it is, it's a bronchus. It's a part of a lung, and the reason it's so small was because it was made for a baby. This particular baby had a disease in which the bronchus collapsed and the baby couldn't breathe enough. And the life of the baby was saved by 3D printing this particular device, this particular object here. It was essentially pasted to the outside of the bronchus, which was thereby kept open artificially, thereby allowing the baby to breathe. It was printed using the EOS printer, which you can see in the corner, which is one of the more modern printers, essentially depositing little particles of plastic layer by layer, allowing you to make very small objects like this with a very high degree of precision. The reason I illustrate this is because it shows one of the most extreme applications of 3D printing. The alternative here would have been death, essentially, death of the baby, because there was no time. But using 3D printing, they could tailor this very specific object with these very specific dimensions, tailored for this very specific baby, and make it in time on the premises. This thing is not mass-produced. You cannot buy it online. So this was really the only alternative. Which sounds amazing, but 3D printing still has some essential limitations. The limitations are the fact that the design process is still relatively slow. And what I mean by that is, if you look at the screenshot here on the left, you can see a screen grab from a CAD program. And what you can bet for sure is that the designer who is making this hasn't been making this kind of thing for the very first time. He's been making this thing or something very similar many times before, over and over again. And the reason this is necessary is because there's no way of reusing existing content. So if I were to compare this to traditional software engineering, probably something that many of you have done is build a website. Well, how would you build a website? You would maybe allocate some cloud space, do a front end using libraries and the back end likewise, and then populate it with content, maybe pictures that you found or purchased online. So if you would compare this to designing a CAD model, the equivalent would be essentially buying your own servers, coding up the whole front end and back end in C based on the specification of the TCP protocol, and have to go out there with a camera and take all the pictures for your website yourself. So this is obviously not very fast, and we want to do better. And the other problem is that it's very related. It's very difficult to find content out there, to find CAD models out there. So the other screenshot that you can see is one popular repository of 3D models called Thingiverse. This is what you get if you look for nails. I mean, not really nails. You have a nail-like object. You have a holder for nails. It's very difficult to find this. So this is the problem that we tackled at my previous company. What you want to do is you want to build an index. You want to build an index. You want to build a big repository of 3D data. And this index should be able to answer certain essential questions. So can you find models of a certain type? Can you find chairs? Can you find nails? Can you find bottles? Can you find similar 3D similar sort of recommendations? Can you reuse certain 3D models? What are complementary 3D models? These are sort of very generic questions, but very important questions that we would like this index to answer. And to do this, what you need is you need a compact and efficient representation of your 3D model. So an example that many of you will know is face recognition. And for example, if you upload a picture to Facebook, then automatically it will suggest the people on this picture based on your friends. And the way this works is not by sort of manually comparing pixel by pixel every image on the whole of the Facebook database. This would be impossible to do in real time. So what instead, of course, you do is you find a compact and efficient representation using specific features with specific invariance properties. So obviously, you want the same face corresponding to a specific person in different poses, to have a similar feature vector. So it needs to have these invariance properties, and what these invariance properties are will define the structure of your index. So this is the approach that we took as well. To begin with, using sort of non-machine learning approaches. So for now on, I'm going to talk about certain approaches that we did, some more, some less technical. I hope they will be interesting for you. So what we start with is basically copying ideas from computer vision. One of the earliest approaches is a light field descriptor. And this is an example of a view-based approach. So what are views? For 3D models, views are defined essentially as being renderings of a 3D model. You look at your 3D model from a specific angle, and you get a render. This is called a view-based approach. And then you apply traditional ideas from computer vision. You can compute descriptors and features on these views, and then you can aggregate them and use this to compare. Now, one issue that you have here, for example, that you don't have for images, is orientation. This is one example of a challenge that we faced. If you look at the screenshot on the left here, you can see essentially this idea of comparing view by view. But because you have multiple possible orientations that your model can be with, you need to look at all possible combinations. And this does not work very nicely in general. So what you'd like to do is find a common reference frame for these objects. And this is possible to do maybe for restricted classes of objects like chairs, because you can tell when a chair is upright and when it's not. But when you have a very varied data set, this is even an ill-posed problem, because it depends on the inherent notion of similarity that you're trying to infer in the first place. So for example, if you're looking for broad outlines, you would align a human being and an elongated car by length, for example. But of course, the car needs to be horizontal, but the human being needs to be vertical. So you need to define a more precise notion of similarity, but this is exactly what you're trying to infer in the first place. So you have a bit of a chicken and egg problem. So orientation is one issue for view-based approaches, for example, and they also apply, for example, to other types of features. And these are non-machine learning based features. For example, heat kernel signature. This is not view-based. It looks at the structure of the mesh directly. It looks at sort of the inherent kind of properties of the model by computing solutions to the heat equation and extracting certain key feature points. These are just examples, but there's a lot you can do with 3D out there, and these are some examples of kind of descriptors that you can sort of essentially concoct without really doing any machine learning. But they have limitations, of course, because the main problem is that they're not very semantic at all. You'd like to understand what makes a chair, and if you have a very small degree of variation, these types of things work quite well, because then you're looking for a very precise match, and these kind of things have the invariance property that you like. But for a class of objects like chairs, for example, which have a very high degree of variability, this won't do. You have chairs of very different dimensions and shapes and styles, but no hand constructed feature will do. And this is something, of course, that's in common with image recognition. So what you do is you look at something more semantic by introducing machine learning, and one very obvious thing to try is a shallow approach. in which you simply introduce weights wherever you can and parameters wherever you can, and you try to infer parameters based on data. So what I have in this screenshot is the Zanika moments that I was mentioning earlier is one specific type of image feature that you can have, which is the spectral composition of your image, if you look at it as a function on the disk. And as you sort of reconstruct your image from this decomposition, you get increasingly high level of detail. So first you have a blob, and then you have, as you add the higher order moments back into the mix, you get something with more and more detail. So precisely because you have this very fine, very nice mapping between lower order moments and lower detail, and higher order moments and a higher, sort of more fine-grained detail, you can try to weight. So you think that for certain classes of objects, detail is more important, whereas for other classes of objects, the broad outline is more important. So this is one thing that I tried, but in practice, again, kind of objects that we were looking at common normal objects, which have a very high degree of variability, and shallow approaches like this don't work so well. So you look at deep learning approaches, and there's two interesting approaches that I want to talk about. One which is sort of doing deep learning directly on the voxel grid. So what are voxels? Voxels are like pixels, but in 3D. And you can define a 3D model by its voxels. So a voxel is 1 if the surface intersects that voxel, and the voxel is 0 if it doesn't. Another approach is, again, a view-based approach in which you look at the rendered views, you look at renderings of a 3D model, and instead you do deep learning on that. So the voxel grid representation doesn't work as well. The rendered views approach works much better in practice, which is kind of counterintuitive, but if you think about the fact that the voxel grid is very wasteful, this makes sense. Why is it wasteful? Well, it's wasteful because most of your voxels are empty, they're 0. Only very few of the voxels have a value, and that value will always be 1. So you're essentially throwing away lots of computation in this representation. And also this rendered views approach, this solves this many issues like orientation that I mentioned before. Because you can simply build a network that aggregates the different views in a pooling layer at a certain level. But the problem is not the approach this time. Oh, sorry. The problem this time is the training data, because there's not much good training data available. If we look at ImageNet, there's sort of millions and millions of images that are very nicely structured that we can use. But for 3D data, you're sort of talking the order of magnitude of tens of thousands of 3D models, and a very small number of categories, so 40 to 55 categories in total, with subcategories as well, which is not ideal. It's not the kind of scale that we would like for deep learning. And often these models are not very clean, which is not really a problem for image recognition, but it can sometimes be a problem for 3D. When you're rendering, for example, you would like a nice mesh with normals, a normal description. Often these models have flipped normals, so adjacent triangles have flipped normals, which is not ideal. And sometimes they just have missing faces and plain sort of nonsense like that, which we don't want. So try bootstrapping, which was mentioned in the first talk today, by combining two different approaches. There are many ways of doing this. One thing, one method I wanted to talk about today was an approach in which you would essentially like to make 3D equal to 2D and use all the progress that was made in 2 dimensions and apply it to 3D, which kind of makes sense, right? Because you can render a 3D model and you get a nice picture. So why not use this directly? In practice, this doesn't work because they're still quite different pictures and renderings, because pictures have all sorts of different backgrounds and noise, which 3D models don't have. 3D models are pure; they're synthetic. But you can kind of go around this by rendering lots and lots of sort of random renderings with random different views, and sort of embedding them all into common space. you essentially fit a representation of your 3D similarity to the 2D images. So what you need in this case is you need a sort of a ground truth. You need a ground truth which is again given by a similarity notion between the 3D models, and then you apply that. You fit that to the 2D images, the 2D renderings, using a deep learning approach. This has some drawbacks too, because you need a similarity notion for your ground truth. You want to say, okay, these two models are similar and these two models are not similar, which has all the pitfalls that you have before. It's not a huge problem if you have a very dense data set of models, but in practice you often don't have enough models available. So again, here you run into the problem of there not being quite enough models and there not being enough training data. Another source of 3D models and potentially training data is 3D photo, 3D scanning. Basically, you can think of this as a 3D photo. And the idea is that you fuse together depth images. A depth image is essentially a picture, but instead of recording the color, it records the distance of the particular object that you're looking at from the camera. And then you can fuse many such measurements together and get a 3D representation. And you can see an example of this in the slide. This problem, though, is this is not enough in a sense. So this is not enough because, why is it not enough? Because if you're talking about 3D, you're talking about pure 3D models. You're talking about an isolated chair. Whereas if I were to 3D scan this room, I would get everything. I would get the floor, I would get the attached chairs, I would get the column, I would get the floor, all in one bucket, essentially. So there's an extra phase which is called segmentation. So there's the reconstruction phase, which is sort of mapping out this room, and there's the segmentation phase. And the segmented model is the final product. So one pitfall is resolution. You tend to get noise. You can see it a bit here already. So you need much better resolution cameras, scanners. Much because in the projection, of course, a small error becomes very big. But that's not the main problem. The problem is that you want to segment semantically. So whereas here it's easy to do because you're simply separating out the surface, in a more complex scene, this becomes much more difficult. So you want to do this semantically. And one approach is to do it as a two-stage process first, and then you try to match the objects in your scene to objects that you have in your database. And another approach is to have a live reconstruction and use the objects in your database to do the reconstruction as well. And this is quite nice because you can decrease the amount of noise that you have in your dataset. But both of these require sort of hand-constructed features, as they did in sort of the non-machine learning approaches. And this is not ideal. We would sort of like to minimize wherever we can hand-constructed features because it's a bit arbitrary. The only way we can assess whether or not they work is by experiment. And there's not a lot of insight involved in that. So we would like to minimize this. So where are we now? Current state of affairs is we have a bit of a chicken and egg situation because to get a better 3D AI, we want better training data. For that, maybe we need better scanners, and so we need more semantic scanners, and so we need better 3D AI. So it's a bit of a difficult problem, a bit of a difficult situation that we're in. How to solve it? Well, maybe using sort of many clever bootstrapping approaches, such as the one I mentioned earlier. These are not ideal because they often require hand-built features, but maybe they'll be necessary in the interim. Maybe better non-AI scanners, and simply more resources being put into this, more resources putting into the 3D digitalization of the world. If a company puts a lot of time and effort into digitalizing their resources in 3D, then they can do it. They can do it even today, but it's just a time-consuming, laborious, and expensive process. And then open 3D data, hopefully. This data will be shared, and to build a truly intelligent 3D AI, it will have to be shared. I think the task of 3D digitalizing everything that is out there is simply too much for any given company or entity. And I do hope that it will become 3D AI, open 3D data. And that will hopefully, that will bring us back to where we started, which is some amazing applications of 3D printing, which I already mentioned. A truly sort of intuitive and software-like style of 3D design. And these guys here having a great time, you can see with a HoloLens, which is virtual reality and its sort of cooler brother, augmented reality, which is an entirely new way of interacting with digital stuff, not just stuck to the screen. So this is a truly exciting new development in industry. So in conclusion, I guess I hope I've convinced you that 3D is important, that 3D is worthwhile doing, that it's challenging, and that it needs AI. So I do hope to see sort of many of you here pursuing this, and that it has fantastic applications, which will benefit us in the future. And I'd like to end with a thought, which is that it's not so much applying AI to 3D as much as it is making 3D accessible to AI. So we sort of made images accessible to AI, we made text accessible to AI. Now as a next step, as a next natural step, we would like to make 3D accessible to the AI. And then who knows what the applications will be, really, the sky's the limit. I would like to end with a bit of a plug, to be honest, and a thank you. So thank you to City.AI, of course, for hosting us. And a thank you to both 3D Industries and the Leo Gibbous Laboratory. 3D Industries for the amazing opportunity to work there for 2 years on this project, and Leo Gibbous for the many fruitful conversations that we've had. So thank you.